everybody. Can you all hear me? Can you all hear me?
Yes, sir.
Yeah. Right. What's the time now? What is the time? Is it 9:30 or still a couple of minutes to 9:30? In my clock, it is 9:30. How about your clock? Is it 9:30 or still we have some more couple of minutes?
9:30.
9:30. So, okay, we will start our lectures because as I said, 9:30 we will be starting. Right. Give me a second. Okay. Last time we talked about, I will share the screen. We try to say that how we can display the data. How we can display the data. So displaying data can be done in different ways. Frequency tables, histograms, bar charts, stem and leaf, box plot, linear graphs, dot plots. Actually, we didn't talk about linear graphs and dot plots. You will learn all these things in your practicals, but we came up to box plot, frequency table, then what are the conditions, rules and regulations constructing frequency tables, and sorry, based on that we can draw bar chart. Actually, this bar chart can be renamed as histogram also. Bar chart and histograms are more or less similar in terms of characters. So bar chart and histograms are same. So we can draw bar chart, class interval versus frequency, class interval versus relative frequency, etc., etc. Then we have seen OGIFs. That is mainly to talk about less than OGIFs and greater than OGIFs. These two OGIFs are based on so that these OGIFs, less than and greater than OGIFs, are based on the less than and greater than frequency table calculations. So that is useful in terms of finding out with some level of probability greater than or less than of a particular value. Yesterday we have seen that how to find out those values. We will see some more later on, especially the probability. This pie chart, it is the simplest form of display. Pie chart can be given in percentage or numbers. So it will give some visual look to see which portion is higher, which portion is almost double or triple, etc., etc. Visually, it will focus. And also we said stem and leaf. This is most important one, where stem and leaf can be single stem and leaf. So this is the single stem and leaf system, where you have only one stem. So that is called as single stem. You have double stem and leaf. These are double stem. So single stem and double stem can be applied. This is double stem. Two stems are there for the same value, right? So this is called as a double stem and leaf. So double stem and leaf could be applied to cases where we have a very large number of data. Then we can go up to even 5 stem and leaf. That is depend on the amount of data that we have, so that we can use 5 stem and leaf as well. If you turn this table, this leaf stem and leaf table by 90 degree, turn onto the anti-clockwise to 90 degree, then it will give a diagram similar to the frequency table. What is the advantage of having stem and leaf? We don't lose any data here compared to the frequency tables. In frequency table, we lose the original data. So that is the difference between the stem and leaf and the frequency table. Then we talked about further some of the measures on display of data. Percentile, decile, then quartiles. Percentile, decile, quartile. Percentile is similar to percentage, as we discussed percentage, right? Decile means it has divided the whole set of data into 10 equal portion. So second decile means it is the left 20% on the left side, 80% on your right side, second decile. Then we discuss about the quartiles. Quartiles mean quarter. Quarter mean 1/4. So it's dividing the whole data set as 1/4, each 1/4, right? Then we consider a set of data. We went through how to calculate the quartile location that is based on truncated median location divided +1 divided by 2. So +1 is coming here, divided by 2. So median location, as we did earlier in this data set, 31 + 1 divided by 2, 16. So truncated median location is again 16 because no any decimal value. So that truncated median location +1 divided by 2, which is 9.5. So this is our quartile location. This is the important aspect of quartile location. So this quartile location is 8.5. So in other term, we can say if you have data here, so the quartile 1 will be in between 8th and the 9th position, right? If you look at the data positions, it will be 8th and the 9th position. Similarly, if you look at Q3, so it will be 8th and 9th position from the backward. 8th and the 9th position from the backward, this direction, right? So that is called as first quartile and the third quartile. That is how we find out these two quartiles, right? So these two quartiles are important in terms of making a plot, which is called as box plot. Box plot is actually giving what sort of data? Yesterday we talked about that. It is giving what sort of data? Middle 50% of the data, right? It is giving middle 50% of the data. Box plot is giving middle 50% of the data. Can you all hear me? Can you all hear me?
Yes, sir.
Okay, right, fine. So this box plot is giving middle 50% of the data. So we can explain how this middle 50% of the data dispersed or spread out, right? So we have Q1, Q2, Q3 quartiles, quartile 1, 2, and 3. For the above data or above example, we have Q1 of value 17, Q2 of value 19, and Q3 value of 20 from our example, right? Now let's look at how this Q1, Q2, and Q3 placed based on the scale. So Q1 is 17, Q2 is 19, and Q3 is 20. So you see here how deviation from this. So this is middle 50% of the data, right? I will be using the board now, right? I will be using the board. So it says this is our box plot. The value is 17, 19, and 20. Can you all see the board? Can you all see the board? Yes?
Yes, sir.
Yeah, fine. Now you see, here we have 25% of the data. Here we have 25% of the data. On the right side, again, we have 25% of the data, which we don't know actually how it has been spread. On the left also, we have 25% of the data. That is also, we don't know how it has been spread out. So we know only the data in the middle, that is 50%. Now, how we can comment about these 50% of the data in the middle? Look at in between Q1 and Q2, and in between Q2 and Q3. What can you say about these two features? Where the in between which Q1 and Q1 in between which Q the data is more spread? Is it in between Q1 and Q2 or Q2 and Q3? Where the data is more spread?
Q1 and Q2.
Q1 and Q2. Why? Because you see the values here, 17, 19. The difference is 2. So the deviation scale for 2. Here, what is the difference? The difference is 1. So the scale is very narrowed down. So, for example, we can draw a graph simply like that, right? If you draw a graph simply like that, this graph is different from the graph that I drew like this. Is that graph is different from that? If so, what is the difference? What is the difference between these two graphs? What is the difference between those two graphs?
The area is different.
Yeah, what is the difference?
The area is different.
Areas are different. Okay. What can you say about this graph? If you precisely
Equally spread.
fine. So this graph, you see, more or less, this distance is equal to this distance. Is it more or less? Right. So that this kind of graph is called as symmetric. This kind of graph is called as symmetric graph. What about this graph? Is it symmetric? Yes or no? Is this symmetric?
No.
No, this is asymmetric or not symmetric. This is not symmetric, or we call it as asymmetric, right? So based on that, we call it as distribution. The term distribution, for example, let's say I have a bar chart. Can you remember yesterday we talked about bar chart? I'm simply drawing something typical one. This is class interval. Let's say this is relative frequency or frequency. This is frequency. This is class interval. Right? Now I connect all the middle point of the bar chart. If I connect all the middle point of the bar chart, that is look like this. Okay. Now I erase simply all what I have given as a bar chart. Right? You can erase and see all the bar chart. So this is what we call as distribution. This is what we call as distribution. You see now no more bar chart, isn't it? Right? So now you see here there's a huge distance between these 2 points. How these 2 points have come? Those are the middle value of each classes. Middle value of each classes, isn't it? Middle point, rather than saying middle value, middle point of each classes. Now, if the class interval become narrow and narrow, the number of classes, we can have very large number of classes. If you have very large number of classes, we can have large number of points. When you have large number of points, that will make the graph very smooth graph. That will make the graph very smooth. When you have large number of points, that will make the graph very smooth. So if you have large number of classes, that means the class interval is very narrow class interval. If you have very narrow class interval, you can have a large number of classes, which is going to be a smooth curve. So that is called as distribution. So if I call what is distribution hereafter, you should understand what it is, right? Right, now this is what our example says, right? This is the place where we stopped last time, right? Now we will move to little on explanation of box plot. So we are going to talk about the explanation based on the skewness. So that term, skewness, right? What do you mean by skewness? Skewness, anyone? Anyone? What do you mean by skewness? Sahana, are you around?
Yes, sir.
Yes, what do you mean by skewness? For example, you see, if I draw a middle point here, is it symmetric? This, Sahana, is it symmetric?
No, sir.
No, it is not symmetric. You see, if I look at the width of these two, let's say, suppose I will draw the width somewhere there, right? If I look at the width here, right? You see, the width are not equal. At every point, the width are not equal. Maybe in some points, the width may be equal, but not in every point. So this feature is called as skewness. What about the skewness here? Do we have a skewness?
No.
No, because if you look at the width at any point, the same. If you divide the graph in the middle, if you look at the width is more or less same in both sides. So there's no skewness, right? Again, if you look at the skewness here, it has skewness, right? So that skewness we can identify from the box plot. So here the box plot, the Q2, which is exactly on the middle, right? Which is exactly on the middle, so that there's no skewness. But in the here in this box plot, for example, if you draw it like this is reflecting here, isn't it? So if you draw it like this, the the spreadness between Q2 and Q1 will be much higher compared to Q2 and Q3. So that skewness is called as a left skew. Sometimes it is also called as negative skew. It is negative skew. Left skewed or negative skew. Similarly, if you draw it for this one, what skewed is like that? What is the skewness there? It is a right skew, because you see that this is the portion that we are looking for skewness. So this is a right skew. So this is a right skewed, or we can say it is a positive skew, right? So middle 50% of the data, how does this middle 50% of the data behave? Whether it is a right skew, whether it is a left skew. In our example, our example, is it a left skewed or right skewed situation? In our previous example, is it a left skewed or right skewed? Left skewed, right? So you understand, sorry, is it a left skewed or right skewed? I try to confuse you. Huh? It is because the distance between Q2 and Q3 is much less, so it is going to be left skewed. Correct, right? So this is, it's look like similar to this diagram, right? So that it is left skewed. So middle 50% of the data can be said whether it is a left skewed or right skewed, right? Right. Give me a second. Right. Now, earlier we talked about only one thing. What is that? What is that? Box plot. What does the box plot does? What is doing this box plot? Using box plot, what sort of data that we can explain? Which portion of the data that we can explain?
50% of the data.
Yeah, which 50% of the data?
Middle 50%.
Exactly, middle 50% of the data we can explain using box plot. Now, again, there are 50% data remaining. We are 25% on your left and 25% on your right. What to do with that data? To explain that data, we need to consider the other technique called as Whisker plot, right? Two types of plots are there. One is box plot. The other plot is called as Whisker plot, right? Is it clear? So box plot explaining only middle 50% of the data. Whisker plot explaining the rest of the 50% of the data. What do you mean by rest 50% of the data? That means 25% of the data in your left side. I will put it as L. The other 25% of the data on your right side. So this is how the box plot and Whisker plot works. This box plot explaining 50% of the data in the middle. So altogether, we can explain 100% of the data. Right. This is how a typical box plot looks like. once you use the what do you call software, it will explain what is box plot, right? It will give by graphically what is box plot, right? Can you remember we talked about a data called as outlier? Yes? Tarshika, can you remember? Tarshika, are you around? Tarshika Vidyakumar. Tarshika. What about Tarshika? Is she absent? Tarshika Vidyakumar. Maybe absent. Right. Subaraj.
Yes, sir.
All right. Can you tell me what is this outlier? What do you mean by outlier?
Sorry, sir.
Yeah. What is outlier? What is outlier? Mute yes. Subaraj, what is outlier?
Sorry, sir. Don't know.
Huh?
Sorry, sir. Don't know, sir.
Don't know? Are you Tamil or Sinhala?
Tamil, sir.
Tamil. Right. Outlier and enna முதல் நாம் விளங்கப்படுத்தியிருக்கனே முதல் கிளாஸ்களுக்கு வர இல்லையோ
வந்தா சார்
வந்தா விளங்கல என்ன outlier என்ன outlier என்ன what do you mean by outlier? Outlier mean that particular data is not behaving similar to the rest of the data. Anyone can you answer what is outlier?
Any number behave out of the range of that other rest numbers.
Exactly. So that is outlier, right? So if, for example, if I measure the height of different people, if I say 172 centimeter, 160 centimeter, suddenly I have a value of 1744. So will it possible to have a value like this in a data? So that is an outlier. So this outlier can be seen using this Whisker plot. So this is how we indicate the outlier in the Whisker plot. This is on a scale, you see. This is on a scale. This is how we indicate the outliers. This is called as mild, M-I-L-D, mild, M-I-L-D, yeah? Mild outlier. This is called as extreme. This is called as extreme outlier. This is called as mild outlier. You see, mild outlier means it is much closer to the box plot, box and Whisker plot. This is the box and Whisker plot, so that we can indicate the outliers. Automatically, computer does this. We can calculate and do it. So otherwise, we can get it from the computer. So this is an extreme outlier. How does this extreme outlier indicated in a graph or box and Whisker plot graph? Like an asterisk. The mild outlier it's indicated using a dot or the small circle. That is how we indicate the mild and the extreme outlier. So this is a typical box and whisker plot, right? Right, now I'm going to, I have a small meeting, JICA meeting, where the dean has invited me also for that meeting. I am going to attend the meeting there. So most probably in half an hour, I will be back, right? If you want to log out and come at 10:30, right? You can charge your phones and come back at 10:30, right? So I'll be back at 10:30. Okay, you can have your breakfast also if you want, and come back at 10:30. I will do the rest and look at the calculations. Just have a look at these calculations. We will do it once we come back, right? Okay, we'll meet at 10:30. We'll continue with where we stop. Right, this is the box plot, box and whisker plot. As I pointed out earlier, we have outliers, right? Outliers, how we define the outliers? The values which are not behaving with the group, basically. So this is an outlier, this is an outlier. You see how far these outliers are deviated from each other. So this is an outlier which is an, yeah, how do you call this outlier? How do you call that outlier?
Middle outlier. Middle.
Once again.
Mild.
While what?
Mild outlier.
Mild outlier, not middle. It is mild. M-I-L-D. Mild outlier. Fine. So this is mild outlier. What about this? Extreme outlier. It is called as extreme outlier. So we have two outliers of a box and whisker plot. Right. We will practically we will do a box and whisker plot and see what are the outliers, and we try to do it. That is what we are going to do it now. Right. To get that box plot, we need to do some calculations. We need to do some calculations. What are those calculations? Some of the calculations we have already done, right? Some of the calculations we have already done. Let's look at other type of calculations, right? The upper limit and the lower limit. In a box plot, what are the upper limit and the lower limit? We drawn a box plot, you see. So this is Q1, that is the lower limit. Q3 is the upper limit, isn't it? So upper limit is Q3, lower limit is Q1, right? Right, we are introducing a term called as IQR, interquartile range. What is that? IQR, interquartile range. So this interquartile range is important. How do we calculate the interquartile range? That is Q3 minus Q1. What is Q3? Q3 is 20 minus Q1, which is 17. So 20 minus 17, which is 3. So what is our interquartile range, IQR, in our given data, which is 3. Right? For a given data, it is constant. Q3 minus Q1. Then we have a component called as scale factor, SF, scale factor. This scale factor is actually interquartile range IQR multiplied by 1.5. You may ask why we multiply by 1.5. This is called as pseudo standard deviation. Don't ask what is pseudo standard deviation. Now, you know what is the meaning of standard deviation, but pseudo standard deviation, right? Pseudo standard deviation. Pseudo standard deviation, we usually take the value as 1.5. So we multiply by 1.5 to get the scale factor. So our scale factor is 4.5. Clear? Is it clear? So these are some of the calculations that we are looking at, right? Then I will erase these things. Now we need to have, give me a second, there's a call, I will come to that. Right. Okay. And lectures and meeting. Okay. Right. Right. Okay. The scale factor, which is IQR into 1.5. IQR into 1.5. So scale factor is 4.5. Can you all hear me? Yes? Can you all hear me?
Yes.
Right. Okay. So scale factor is IQR multiplied by 1.5. Right. Now we want to calculate some other components. Those are called as lower inner fence, lower inner fence, lower inner fence, right? Lower outer fence, upper inner fence, upper outer fence. We have 4 components. Can you all just see how to calculate all those? Yeah, how can we calculate those different fences? How can we calculate those different fences? First, the lower inner fence. Lower inner fence, LIF in shortened form, calculated by Q1. We know already what is Q1, right? Q1 is there. Q1 minus the scale factor. Scale factor we already found. So Q1 minus scale factor, that is the value. So our lower inner fence is 12.5 for the given data. Then lower outer fence, right? That is, it should be lower outer fence. Huh? This is not, yes, this is correct. lower outer fence LOF is equal lower inner fence minus scale factor again. Or otherwise, we can say Q1 minus 2 scale factor, the same thing, because here we are deducting scale factor. Again, we are deducting the scale factor. So lower inner fence, that is the value of 12.5 minus the scale factor. So we end up with 8. So lower outer fence is 8 for the given data. Similarly, we can calculate the inner fence for upper, right? Outer fence for upper value, right? Inner fence for upper value and the outer fence for upper value, right? So that is based on Q3 plus scale factor. So Q3 is 20 plus 4.5. Then we calculate the value for upper outer fence. So that is outer upper fence, right? Upper outer fence will be upper inner fence plus scale factor. So that is 24.5 plus 4. So those are the upper inner fence and the upper outer fence values, right? Right. We will just look at the board. Look at the board. What do you mean by this inner fence and the outer fence? Let's identify these terms: inner fence and outer fence. Those inner fence and outer fences are imaginary values, right? Imaginary lines. So we have the box plot. This is Q1, Q2, for example, Q3, right? So we say this is upper inner fence. I will put it as UIF, upper inner fence, upper outer fence. This is on a scale. This is on a scale, right? Similarly, you can have lower inner fence and lower outer fence. You see, these are imaginary boundaries. This is not the final box and whisker plot. This is not a final box and whisker plot. I will show you final box and whisker plot later on. So this is just to give you why we want to calculate this outer fences and the inner fences for left and right side. So this upper side and the lower side. All right. So that we have already calculated. Okay. This is upper inner fence. Upper inner fence is Q3 plus scale factor. Upper outer fence is upper inner fence plus scale factor. Similarly, left inner fence Q1 minus scale factor. Look at your notes. Then lower outer fence is lower inner fence minus the scale factor. So that is how it incorporated. Right? Let's move to the rest of the calculation. Any questions? Any questions? So these are just calculations from the same data that we have used earlier. Right, now we have two more things that we'll have to calculate. That is called as upper adjacent value and the lower adjacent value. Two things has to be calculated. Upper adjacent value and the lower adjacent value. What are those adjacent values? Look at the definition very simply. Upper adjacent value. Upper adjacent value means it will be on the upper side. Lower adjacent value means it will be on the lower side. Upper adjacent value and the lower adjacent value. Upper adjacent value is the largest value below upper inner fence. right? Largest value below upper inner fence. So the largest value below upper inner fence. So this is the upper inner fence, the largest value, all right, on the upper inner fence. So the value has to be closer to the upper inner fence, right? The larger value which has to be closer to the upper inner fence. So it should be closer to the upper inner fence. It should be largest value, right, below the upper inner fence. Similarly, you can see the lower inner fence, it is the smallest value above the lower inner fence, right? Smallest value above the lower inner fence, right? Okay, is it clear? It is the smallest value above the lower inner fence. So we can say, actually, you can say that is above lower inner fence. Yes, smallest value. You can change this. Below lower inner, I mean below me it is upper, right? What do you mean by this term? Let us be very careful with this term. This above. What do you mean by this above term? Above term, smallest value above lower inner fence. Smallest value above lower inner fence. So what is the lower inner fence? Lower inner fence is this one, right? Smallest value. It's coming somewhere. Right? So this is how we can indicate the adjacent values. Lower adjacent value and the upper adjacent value. Now, these are the only calculations that we do. These are the only calculations that we do from the data. So from here to here, these are the only calculations that we consider. So these are not calculations. These are observations based on the calculations, right? So next one is how to look at the mild outliers, mild and the extreme. How to look at these two outliers. In simple term, mild outlier, can you remember earlier I have showed you mild outlier and the extreme outlier. Two types of outlier, mild and the extreme. So how we account the mild outlier? It is the value between the inner fence and the outer fence. So if there is any value between the inner fence and the outer fence. So you could see here, if there is an outlier, mild outlier, I can indicate as such. This is how I indicate the mild outlier. Okay, this is how I indicate the mild outlier. Look at the other outlier, extreme outlier. What is the definition for the extreme outlier? Any value above the outer fence, beyond the outer fence. So here, any value above the outer fence or any value below the lower outer fence, below the lower outer fence, because it is on a scale. So we can indicate, this is how we indicate the extreme outliers. This is how we indicate the extreme outliers. Okay. So you have already seen in a previous sample of box plot the extreme outlier and the outlier which is inside the inner fence and the outer fence, which is called as mild outlier. In our data, if you look at, if you just get the values for adjacent value, right, and left and the right adjacent value, or the upper and the lower adjacent value. So these are the adjacent values. So this is the upper adjacent value. This is the lower adjacent value. Right? From our data, this is the adjacent value. Look at those values. What about the mild outlier? We said it is in between inner fence and the outer fence. Doesn't matter whether it is upper value or the lower value, lower side or upper side. So we will come across an outlier which is as 29. The value 29 is an outlier, which is a mild outlier in our example. What about extreme outlier? Extreme outlier, it should be go beyond the outer fence. What is the outer fence values? Both. Upper outer fence value is 29. Lower outer fence is 8. Is there any value in our data less than 8 or greater than 29? Can somebody tell me, is there any value higher than 29 and lower than 8 in our data? Yeah? Kamsatani? Do we have any data below 8 and above 29 in our data set? What is our data set? Sorry. What is our data set? This is our data set. Look at our data set. So do we have any value below 8 and above 29?
No, sir.
No. So that is the margin, right? So our outer fence is, lower outer fence is 8. The upper outer fence is 29. So we don't get any value below 8 and above 29. So we don't have extreme outlier. We don't have extreme outlier. Right? So that is how we can conclude our box plot information. Right? Right. Now, these are some of the definition. So the outer value, inner value, extreme value, mild outlier, adjacent value. What is the adjacent value? It is the value which lies between the quartiles and inner fence, which is closest to the inner fence. Which is closest to the inner fence. Right? So that is by definition. So the value between this quartiles and inner fence, which is closest to the inner fence. So in other term, for example, this is the inner fence, whether it is a lower and upper. What is the value? What we call it as adjacent. Adjacent values, it is in between the inner fences and the quartiles. So this is inner fence of left is here. This is the quartile. So it should be in between this, and it should be the upper one should be in between Q3 and upper inner fence. So it should be in between these two gaps, but closer to the upper inner fence. So this is how we indicate, for example. So these are the adjacent values. These are the adjacent values. So what this adjacent value? Almost 90% or almost 99% or almost 100% of the data falling into this category. So this is upper adjacent value, lower adjacent value. If you connect these two, it says that almost all the data falling into that range of adjacent values, right? The lower adjacent value lower adjacent value, somebody has said, let's look at it. What is the adjacent value? By definition, lower adjacent value has to be in between the left inner fence and the Q1. Right? What is our left inner fence? Sorry. Left inner fence. What is our left inner fence? The lower inner fence, that is 12.5 and 12.5 and 17, but it should be closer to the 17. It should be it should be closer to 12.5 in this case. It should be between 12.5 and 17, but closest to 12.5. Let's look at the data. What is the value in between 17 and 12.5? 17 and 12.5. We have 16, 15, 14. Yes. This is 18. Yes. No. 17, 16. 17, 16, 15, 14. Yes, fine. The value, you are right. This value, change this value as 14. Right? Change that value as 14. This should be 14. Somebody already indicated. I have done a mistake. So that should be 14. Lower adjacent value is 14. Right? Can you all see me? Is that correct? Lower adjacent value should be 14. Right? This is 14. Right? This is 24 according to our calculation. Right? So the upper adjacent value should be closer to the upper inner fence. Lower adjacent value should be closer to the lower inner fence. So that's fine. Okay. Yeah. Okay. Right. Fine. Any questions on this? So these are the definitions by word. You can write down. I mean, already you have all these definitions. Adjacent value. It is the value which lies between quartiles and inner fences, which is close to the inner fence. Mild outlier, the value between inner fence and the outer fences. Right? So do we have a mild outlier in our example? Yes, we have a mild outlier, only one. What is the value of mild outlier? Anyone? What is our inner fence? Inner fences. Look at the inner fences. Inner fence and the outer fence. That is in between 12.5 and 8. Is there any value in between 12.5 and 8? On the left side or the lower part? Do we have any? Hello, do we have any value between these two? Do we have any value in between these two in our data? Yes or no?
No, sir.
Yeah?
No, sir.
No. Now I'll have to read
No,
the
sir.
names. Right?
No, sir.
No, right, fine. What about the right side or the upper value? Is there any mild outlier in between these two? Because this is the outer fence is 29.
Yes.
Yeah, inner fence is 24.5. So what is the value do we have as a mild outlier? 29. Right? We have 29 as mild outlier. Okay. Right. So anything questions on this? So the mild outlier we indicate by putting a circle. Extreme outlier, right? We put by asterisk. So you see here, mild outlier we put by. This is how we indicate mild outliers. Extreme outlier we indicate by that. Right? You can read that. Right. So this is actually the diagram for our example. This is actually the diagram for our example. Actually, this has been drawn by a software. Right? Can you guess what is this value? Can you guess what is this value? Is this border line? The value of this?
12.5.
No. I said adjacent value.
14.
Yeah, adjacent value. Earlier I have mentioned here that is the range of data that we have adjacent between adjacent values. Yes, that is 14. Somebody corrected because I made a mistake manually, but computer didn't make a mistake. So adjacent value is 14. The left adjacent value is 14, right? I use the pen. Left adjacent value. This is actually, if you look at the scale here, it is 14, right? What about right adjacent value? What is the value?
24.
24 or 24.5. I'm not sure. What is the value? 24. Right. Okay. If it is 24, okay, fine. We have already calculated that. So you see, all the data, almost 100% of the data are falling into this category. What can you say about our quartiles? This is Q1, this is Q2, this is Q3. Is it symmetric? What can you say about where it is skewed? If it is symmetric, no problem. Can you say whether it is skewed? Whether it is skewed?
Yes, sir.
Which side it is skewed?
Left side.
Left side, yeah. So this is skewed to left side. I will come to that. So if you draw a graph like this, you see, so this is not symmetric. Here it is skewed, isn't it? Right. So this is the right or the upper adjacent value. What is this then? What is that? That is,
Mild outlier.
yeah, that is mild outlier. That is mild outlier, right? So that is mild outlier. So this is how we indicate. No problem. This is the box plot. Is it box plot or box and whisker plot? If it is box plot, you will draw only this, nothing else.
Box and whisker.
Yeah. If you draw only this, that is box plot. This is box and whisker plot, right? So now we can describe our information, box and whisker plot, using this information. Few things. What about the middle 50% of the data? Is it symmetrically distributed? No, it is not symmetrically distributed. This middle 50% of the data is skewed to which side? Left side. Skewed to left side. Middle 50% of the data skewed to left side, isn't it? So that is obvious. Right. What do you mean by tails? Tails mean these are the tails. Here we have 25% of the data. Here also we have 25% of the data. Which tail is longer? If I say this is a right tail, this is a left tail of the distribution. Which tail is longer? Tails are more or less symmetric, isn't it? Tails are more or less symmetric. If I draw, for example, a box plot, if the tails are looks like this, where the tail is longer?
Right side.
Right side. So when the sorry, I will draw it once again. So this is a box plot. So here, right side the tail is longer, so that we simply say right. I'll put it as a right tail. Huh? I'll put it as RT. Right tail is more random. Write down. In this case, write down. Right tail is more random. That means more random means right tail is longer. Right tail is having more values than left tail. Right tail is more random. But in this example, more or less this distance and this distance more or less same. So that we can say tails are more or less symmetric. Do we have mild outliers or extreme outlier? What is this? This is a mild outlier. So we can say there's one mild outlier. Since there is no extreme outlier, we don't need to report it. If there is one extreme outlier, we need to report that as well. Okay. So in this case, we simply say the tails are more random. I mean, right tail is more random than the left. Any questions? So this is how we indicate or describe the box plot. Yes or no? Before we come to the other portion. Have you all understood? Yes? Have you all understood the box plot? Yeah? Kamaladeepan, are you around?
Yes, sir, I am here.
Yeah.
Understood. Understood, sir.
Okay. Right, fine. Then we will move to a little on description on further distribution. I have already mentioned the distribution. When you talk about distribution, it includes the whole set of 100% data. Not only the middle 50% of the data, it includes all 100% of the data. All right. So if you look at the data distribution, we can discuss that distribution in terms of skewness. I have already introduced the term skewness. Skewness means how that particular tail is distributed, whether it could be on right or on left. To see statistically whether that data is having any skewness, we have a simple formula that is called as K, which is given as coefficient of skewness that we can measure. Coefficient of skewness is 3 into, what is this? Kamaladeepan, what is that?
Samples.
No, I'm asking what is this? What is that? In English, what is that? First of all, identify what it is. X bar.
X bar. Oh.
What is X bar?
The sample.
Sample. One more word is missing.
Sample bar.
Sample bar. This is not ice cream bar. This is not magic ice creams. Bar. by screen. So what is
Sample mean.
sample mean? Right. Sample mean. Right. Good. Sample mean minus, what is this again? What is this? What is this? Kamaladevan, what is this? Huh? Kamaladevan,
Yes, sir.
are you following?
Yes, fellow.
Yeah, what is this? What is that?
Me,
Huh?
medians.
Yeah, what is that? Median. Median. So this is mean. We have already talked about mean, right? Sample mean. This is median. MD mean median, right? I will clear it. So mean minus median. What is this, Kamaladevan again?
Sample.
Huh?
Skew.
What is that?
Skew. Skewness.
Once again, I don't hear.
Skewness.
No. Skewness that we do measure using this K. That is the skewness. But I am asking S. We have learned this is in first or second class. What is this? For a data set, if you have given S, what is that? Nalla notes of purati paathattan theriyum. What is that? Anyone? Anyone else? What is this S for a data? For a data set, what is this S? What do you call this? Sharma, are you around? Sharma, Miss Sharma. Samiksha Sharma. Are you around? Samiksha Sharma is missing, huh? Are you not around? Paragunan, are you around? It looks like all are absent, huh? Dilhani. Dilhani, are you around?
Yes, sir.
Yeah, what is this S?
Sample standard variation.
Halfly correct. The last part is missing. What is that? Sample standard? No, not variation. Sample.
Deviation.
Yeah.
Deviation.
What is the difference between this and that? This is sample standard deviation. This is sample variance. This is square is sample variance. Right? There's nothing called standard variation. Right? This is sample variance. This is sample standard deviation. Right? Okay. Okay, right. Fine. So this is an important information to measure the skewness. Right? To measure the skewness, that is one of the important important formula. So that is given as a coefficient of skewness. Right? Right. I will come to a typical graph. Look at this. Is how do you call this graph? How do you call this distribution? It is a distribution symmetric. Symmetric distribution. So I said here, if you measure in both at any places, the width will be same. Here or here or here, wherever it is. If you measure, the width is same. So it is symmetric distribution. Right? So this is in a symmetric distribution. What can you say? What are these? What are these values? How did, under which category that we have learned this measure of center, isn't it? Mean, median, and mode. So this mean, median, and mode will be lies more or less in one place. Mean, median, mode lies only in one place. Right? Mean, median, mode lies only in one place. So that is it is symmetric. But if it is not symmetric, for example, let's say, how do you call this? What skewed? Positive skewed or right skewed? Yes, I will put it as R. Huh? It is right skewed or positive skewed. So in a right skewed, mean is somewhere here, right? Then you have median. The peak is mode always. The peak is always mode. So in our calculation, mode is not coming into picture, only mean and the median, right? Mean and the median. So what can you say about mean is higher value than median, isn't it? Mean is, right, here we have X bar in this case. Oh, I will write it as mean is higher than median. I will put it as MD, right? Mean is higher than MD. So if mean is higher than MD, what can I say about this value, whether K is positive or negative? Don't worry about the value, no? Whether K is positive or negative. If positive. So here we have a positive value. K will have a positive value. What about here? I forgot to tell that. What about K here? What value K most probably? The value of mean and median are more or less same. So that what will happen to the value of K? If it is symmetric, K will have a value more or less 0. Right? K will have a value more or less 0. What about here? Here mean is less than median. Right? Mean is less than median. So what can you say about K? Is it plus or minus? Mean is less. So it is mean is lesser value than median. So what will happen here? K is equal. K is equal minus or plus? It will have a negative value. Right? So that is how we can express the distribution. Right. Now let's say I have a value of K equal 0.5. Another example, another data set, I have K is equal 2.5 value. Huh? What can you say about this data set 1 and data set 2? What can you say about these two data sets? Which is more skewed? First thing, whether it is a right skewed or left skewed, positive or negative skewed.
Positive skew.
Yeah, both cases they are positive skewed because they are positive value like this. Second point, right? Both are positive skewed. That is first point. Second point, which one is more skewed? More skewed, whether this or this.
Second one.
Second one, yes. Why? Because it has a k value of 2.5. The first one is having k value of 0.5. So this is less positive skewed compared to this. So whenever the value comes closer and closer to 0, the skewness is less. So this is positive value, the negative value, for example. So if you go in this direction, right, or in this direction, the skewness increases. Doesn't matter whether it is positive or negative skewness, but skewness increases, right? Okay, so that is about the skewness of any distribution. So, right? How many of you have, you can withstand for another half an hour? We started at 10:30, right? After 10:30. So shall we continue till 12? Another maximum half an hour, maximum 12. Huh? Shall we? Yes or no? I have 4 or 5 slides, so I can stop that with that. Yeah? Shall I continue? When you are silent, that means you are granting permission to continue, right? So mean of the frequency distribution. Now how to find out the mean for a frequency distribution? Frequency table, for example, if you have a frequency table, how to find out the mean of the distribution? So which is approximated by summation x into their frequency, whole thing divided by n, right? So n mean, it is the summation of overall frequency, where x and f are the midpoints and frequencies of a class respectively. So x is the midpoint, right? F is the frequency. Because, for example, yesterday's sum, we have looked upon frequencies. Yesterday, frequency table, 200 students. So we have 132 to 150 something, 7, 157 to 162, 172. Right? Likewise, we have frequencies. I can remember this 25, this 100 or something. Right? So here, how to find out the x and the f? This is f, this is f. So in the formula, we can fill it to the f. Summation of f is, in our example, 200. No problem there. What is x? X is actually the middle point of these two. What is middle point of these two? That is, you add these two values and divide by 2, for example. Add these two values, divide by 2. That is 289 by 2. So that is our middle point. That is 140, 4.5. So this is my x. This is for the first category. So for the first category, that is 144.5 multiplied by 25 plus the second one is again 164.5 maybe. Huh? What is the value? What is the average of adding these two? Can somebody calculate? What is the value here? 157 plus 172 divided by 2. What is the value? Hamsatvani, what is the value?
$164.5.
Another 54.5. $154.5, right? So this is our middle value. So likewise, you'll have to find out the middle value for all the categories and get the average, right? Okay. So that is how we'll have to calculate it. Right. So we will look at an example, right? So this is mean of a group data that we have already discussed. Right. The midpoint of each value, this I have already shown you how to look at the midpoint, lower limit and the upper limit divided by 2, which I have already discussed with you. Then find the sum of this products of the midpoints and the frequencies. Then you have the total frequency, then you divide by the total number, the simple steps, right? Let's take an example how to find out the values for this. So for the first example, right? So this is the class, this is the frequency. So what is the midpoint? You add these two, divide by 2. What is the midpoint? So 12.5. So we can say 12.5. Write down 12.5 multiplied by 6 plus next one. The midpoint of that is 24.5 multiplied by 10. So likewise, you'll have to include all the values, right? Whole thing divided by the total number of frequencies. What is the total number of frequencies? Somebody? So that is 6 plus 10 plus 13 and so on, right? So we can do that, no problem. So it is already done for yourself. You can multiply this 12.5 into 6, blah blah blah. Then this is 2089 divided by 50, right? 2089 divided by 50. So that is 41.8 minutes. Right. This is the distribution as I said earlier. So if you have the frequencies and you can simply draw the distribution. So this is more or less a symmetric distribution. Why it's called as a symmetric distribution? Why this is called as symmetric distribution? Just draw and see. This is very symmetric. A vertical line can be drawn through the middle of the graph of the distribution and the resulting in halves approximately for the mirror image. If you cut it here, already it is cut there. So you can see 2 halves there. Right. Now, if you look at the another distribution, right? it is called uniform distribution. We may talk about uniform distribution later, uniform probability. So it is uniform, whether it is the values increase or decrease, doesn't matter. This is a consistent. This is a consistent, right? So it is a uniform distribution, right? So all entries or classes in the distribution have equal or approximately equal frequencies. Right, sorry. Skewed distribution. This is skewed to left side that we have already seen. What is a skewed distribution? And this is skewed to left side or negative skew. We call it as this is negative skew. You see, if you draw a line in the middle, this distance are much far away compared to this distance. So this is called as negatively skewed or left skewed, right? Last one probably, this is a right skew, which I have already discussed to you. This is a right skew. It's a right skew. Okay. So if you put up a line in the middle, so you have not equal distance in both sides, right? So this is called as right skew. Right, we'll stop here. Jeffrey, when shall we have our next lectures? Jeffrey, oh, comes up button.
Next Wednesday or Tuesday.
Pardon?
Next Tuesday.
Next